Good afternoon. On behalf of the Jerzy Stelmach Eureka Foundation, which deals with the interactive education and popularization of front-edge scientific research, I would like to invite to welcome you for the session 5 of our discussion forum related to the popularization of the frontal scientific achievements of outstanding scientists. We are dealing today, before yesterday and the day before and tomorrow, with the topic about classical and quantum black holes in the universe. Our project is co-financed by the Polish Ministry of Science and Higher Education under the Social Responsibility of Science program. Today we had the discussion about the singularities in the Einstein's theory and in particular in the context of black holes. Now we are going to discuss the issues related to the physical effects in the neighborhood of the black holes. I would like to welcome my guests, our lecturer, Professor Marek Biesiada from National Center for Nuclear Research. Good afternoon.
Good afternoon.
And Professor Vincenzo Salzano from the Cosmology Group of the University of Szczecin. Hello, Vincenzo.
Hello. Hello.
Uh, this part of the discussion is gonna to be devoted to the physical effects in the neighborhood of the black holes. I would like to ask first question to Professor Marek Biesiada. My first question would be, since we are dealing with physics, not mathematics, as it was mentioned, for example, during the last discussion, but with physics, I would like to ask Professor Marek Biesiada what actually does he understand under the notion of a black hole in the physical sense, and what he means as what is his interpretation of the black hole horizon, also in the physical sense. What physical effects are related to black holes, first of all?
Uh, so what is a black hole? Uh, a black hole is formed whenever the mass is compressed to the size lower than the size of the Schwarzschild radius associated with that mass. And this means, and this will be, the next issue about the horizon. If it is compressed so, it does not represent any physical material body as we usually understood the celestial bodies like planets, stars, the planets which have solid surfaces, some compact stars like white dwarfs or neutron stars have their surfaces. The black hole does not have a solid surface. So one may say that it is the geometry in the purest sense, only gravity. Every matter has been compressed under the event horizon. So the black hole is really a very special object. That all the physical content responsible for its formation has disappeared beyond the horizon. So what is this horizon? Is this a singularity? Actually, no. because, and it was, I think, discussed in details during the previous session, the singularity, we are talking about singularity when the histories of the observer ends. So history singularities are very malicious. I mean, they signal the end of physics. When the history ends, everything ends. But the observer turns out that the infalling particle can freely cross the event horizon. It is the event horizon because of the abilities to communicate with the outside. So when this particle is falling inside, we may imagine, so very often we are doing the thought experiments. It does not actually happen in the nature, but we may imagine, ask ourselves, if we send the astronaut with a spacecraft and we are communicated with him or her very well all the way toward the black hole, but what happens if the spacecraft is approaching the event horizon? Uh, we know that in some supermassive black holes, it is very often one can hear that approaching in the horizon will tear up the spacecraft. The tidal forces will be so huge that the spacecraft or any solid body will be dismantled and destroyed. It is true for the stellar mass black holes, but for the supermassive black holes, where the uh, size of the event horizon is like light weeks, I mean the fraction of the parsec even, then the tidal forces are not so huge. So we may imagine freely that in such a case the spacecraft can cross the horizon without being destroyed. However, and this is I mean the universal truth, were communicated with us. I mean, it will take longer and longer time to get the signals. The signals will be by electromagnetic waves, either by light or by radio. Anyway, I mean, it depends. The only difference is the wavelength, but it will take longer and longer, and these wavelengths could be longer and longer. They could will experience the gravitational redshift. I mean, in short, for me, the black hole is the purest form of gravity. Gravity without matter. Matter is hidden. I mean, not exactly without, because I mean something is responsible for its formation, but all the matter, all the information is hidden, hidden by the event horizon. And event horizon is a horizon for the external observer, not so much a horizon or the singularity for the infalling or traveling inside traveler. As I mentioned, for the supermassive black hole, it may experience crossing, smoothly crossing the horizon, but then it is an inevitable fate to fall to the center. There is no way to stay on the orbit around. The fate is fully destined, is the destination, just to fall and finish in the singularity, because the histories of everything falling inside the horizon will eventually come to an end.
Mariusz, mikrofon.
Yes, I would like to carry on this discussion in a way that we are talking about one horizon. So we are talking about the static black hole, which is somewhat unrealistic. We have heard during our recent debate during the discussion one today, that all objects in the universe actually rotate, including black holes. So the question is, maybe first question is to Professor Biesiada, then the second question about the formation of the under rotation. But the first question to Professor Biesiada: how about if the black hole rotates? Is there any effect that there are more than just one horizon, and why is it so? I mean here just the so-called mentioned already during our discussions and lectures, Kerr black hole. How is it like in the Kerr black hole then?
Yes, indeed, it is a fundamental difference between the static Schwarzschild black hole and the rotating Kerr one, because this rotation uh, causes the appearance of two surfaces, actually two sorts of horizons, and one of them is the event horizon proper, analogous, fully analogous to the horizon of the Schwarzschild. And another one is somehow elongated. They touch together in the polar region, but the another one is elongated in the equatorial plane, is flattened, like the figure of the rotating body. The rotating body usually is flattened at the equator because of this centrifugal force. And the region between these two horizons is called the ergosphere. It's a very interesting region in which the observer cannot remain at rest with respect to this to this black hole, but is forced to rotate. Well, it is also known in relativity that the rotation induces the dragging of inertial frames, and even this effect, it is perhaps not so widely propagated, but these effects has actually been measured around the Earth with the experiments, satellite experiments, very sensitive ones, the gravity probe B, which measured the reality of this frame dragging, very, very sensitive gyroscopes measured this effect. I think it is already a common law to acknowledge that there is a need to take into account the general relativity around the Earth in order for the GPS system to function properly. So maybe not so much this frame dragging, but gravitational redshifts, of course. However, the gravity probe B have proven that the space-time around the Earth already, I mean, it can be proven experimentally that it is described by the Kerr metric. So
Okay.
indeed, I mean, the Kerr metric is the most realistic one, and the rotation, I mean, brings us to the next level of
But
sophistication.
there are still horizons, not only one horizon, there are more advanced or complicated horizons, I understand, not just one horizon, and also the type of singularity for the rotating black hole is different than for the static black hole. So rotation, in fact, matters. So I would like to shift this issue of rotation and come back to the discussion which was actually performed during the last discussion meeting. It's the question which relates to this, to Professor Salzano, how, in fact, how, in what way the celestial bodies can deform during or under the rotation process, and does it affect also the black holes, and in what way the black holes are actually or some strong gravity objects are affected by the rotation. What I mean is if they rotate rigidly or they can deform, or what could happen out of all this. Maybe continuing the discussion from the previous,
Yeah.
but it's related to what we are talking about now, about this
Yes.
more complicated nature of the rotating black holes.
So for the first part, I can share because I have
Yes,
an
yes,
image.
yes, please.
Okay. So for the first part, well, I'm not used to, no, not from here. Yes, of course. The bodies who rotate have some distortion. And basically, for example, here we have a picture of the sun. The sun is made of plasma. Plasma is a particular state of matter. But what is important is that let me be not probably poorly physically correct, but just to let the public understand. Magma plasma is a state which is more, let's say, liquid than solid. So the sun is a mass of gas which is boiling up, actually. And of course, this means that it is not rigid. It's not made of iron or whatever. It's not a metallic. There are different parts which move with different velocities. And actually, it rotates. So this is an experience which everyone knows, I guess. If we start to rotate, and if we hold some, I don't know, bags or whatever, and we start to rotate, we can see that where where at the end of the arm, the bags or whatever, they are pushing us. Pushing us means that we feel a force stretching in this direction. If we could, for example, I make an example which is stupid, but let me pass it to make you understand. If we attach not only bags to our hands, but also to our ears, and we rotate, we will also feel something stretching the ears, but much less than the arms. And that is what is happening and what is written here in this picture. Imagine this is the sun and it is rotating vertically, right? So imagine that now we are going to put, I guess you can see the arrow. Imagine that you are going
Yes.
to put here stones from north to south. What happens? Well, whatever is closer to the equator rotates faster than what is close to the poles. So you can see that, for example, after 25 days, the stone which was here actually will be here. And in 25 days instead, the stone which was here has not arrived to turn on the back. So that happens because sun is not a rigid body, we say in physics. So is, let's say, liquid plastic. And this, the effect of the rotation, you felt more on the equator than on the poles. And I want to say something more, because even Earth is distorted by its own rotation. This may sound strange because we are used to the Earth crust, which is solid, no? But actually, if you cut the Earth crust, respect to all the rest, is negligible. So, on top of this peel, we can say the skin of the Earth is just the crust, and that's the only solid part. But below the crust, there is a lot of magma. Magma, it was come out when there are volcanic eruptions, and that's liquid. So Earth is rotating. You can imagine that this liquid inside pushes the crust more in the same way as sun, more at the equator than at the poles. And I have a curiosity for you now, because let me, how to exit, sorry. Because now I will ask, what is the highest mountain on Earth? Everybody, I guess, will reply Mount Everest, because it's almost it's 8,800 meters. Well, it depends on the perspective. For example, here it's Mauna Kea is the volcanic, is a Hawaii island. And what is the difference between Mauna Kea and Mount Everest? Mount Everest is 8,800 from sea level. Mauna Kea is, respect to the sea level, is just 2,000, 3,000. But if you consider, if you go below the sea level, Mauna Kea starts from 10,000 meters. But then now there is the curiosity. Actually, from where we count, technically, one could say, if we want to count the highest point on the Earth, we should start from the center of the Earth, not from the sea level. If we count from the center of the Earth, then the highest mountain is this mount in South America, Chimborazo, which is only 2,000 meters. But because the Earth is rotating vertically and it is pushed to the equator, this mountain is located close to the equator. So it is farther. As you can see here, the dashed line should be the Earth, not rotating. But because the Earth is rotating and the magma is pushing the crust, the actual shape of the Earth is this sort of ellipsoid. Actually, it's called geoid, if I'm not wrong. And in close to the equator, the magma pushes more the crust. And then we can say that Chimborazo is the tallest mountain if we count the distance from the center of the Earth. So, of course, as I told you, everything rotates, and also black holes. I'm quite sure, I'm not an expert on this, but I'm quite sure that all black holes should rotate. And that's the point. The point of this is the same mechanism which I told you before that creates stars is also at the beginning of the life of a star. Because let's take the sun. The sun rotates. Then stars are now, what are stars? There is an equilibrium between gravity, which want to push everything in, and there is this thermal pressure, because inside the sun, inside the stars, inside our sun, there are a lot of thermonuclear bombs which are exploding, which push out. So when we have a star when there is equilibrium between gravity, which want to push, and this radiation pressure, which push out. Now, unfortunately, in some billions of years, the fuel, which is burned by the sun, will finish. So what will happen? There will be not anymore any radiation pressure to the outside. So there will be only gravity. What happens? Gravity will start to collapse. What happens when it collapses? Pushing, crushing the matter. There will be a sudden explosion, because if you crush something, the temperature are raising. And what will happen with stars is that they will explode. What is left? In the case of the sun, what will be left is a white dwarf. It's called white dwarf because it's dwarf. It's a very small star, and it's white because it's very bright. For stars which are a bit larger than the sun, when they will explode, what will be left is a neutron star or pulsar. When you have stars huge, when they will explode, what will be left is a stellar black hole. So now remind this picture of the ice skater. The sun is rotating. What will happen to the white dwarf? The sun is this, the white dwarf will be like the skater, ice skater closing the arms. So the part of the rotation which the sun has will be also transferred to the white dwarf, which will rotate very fast. That's the same also for pulsars, neutron stars, and for black holes. Black holes, which are formed from collapse of stars, must rotate because there must be this. This is in physics conservation of angular momentum, conservation of energy, and things like this. Because the initial star was rotating, there will be also rotation in the final state. After the death of the star, there will be what is left, in this case, black hole, it will rotate. About the formation of black holes, honestly, I'm not sure. I mean, for sure, there will be a different, as you anticipated, and maybe as we will say in a few minutes, there are many horizons around around the black hole. If it is rotating, what happens is that these horizons have a different shape. So if we are asking me if there is a deformation of the black holes itself, honestly, I don't know. Maybe you know better than me. But in terms of the horizons, the many horizons which are outside, yes, of course, they will change. They will have a different shape, and so in somehow rotation has influence on that. About the black hole, honestly, I'm not an expert on this. You may.
Maybe Professor Biesiada can more comment about how a black hole is formed actually in the context of this rotation, because I mean we usually show the picture where there is this cloud of particles which actually fall into each other and then form kind of a static one. But how about this rotating case? How this is this can be commented on? Uh, yes.
Yes, of course. I mean, as already mentioned, all celestial bodies, the stars rotate. So black holes are believed.
Yes, we were disconnecting Professor Biesiada. Okay, so uh, it seems
It's
that
probably
yes, we are disconnected. Okay, now it's okay.
And now it's okay. Okay, so every star is rotating. So black holes, stellar mass black holes are believed to be formed in the supernova explosion. So the prosupernova star is rotating itself. And then, as you may imagine, and it was illustrated by Vincenzo with this picture of the ice dancer and making rotating faster by not stretching, but I mean putting the hands toward the body. So something happens with the collapse. I mean, the interior collapses, and what is formed and left behind is rotating. And we have a pretty good evidence for that because not only black holes are formed with supernova explosions, but also the neutron stars, and some of them are observed as pulsars. And pulsars are rotating very fast. So the fastest rotating pulsars are millisecond pulsars. So they are rotating very fast. And whenever the remnant has the mass exceeding for the neutron matter to maintain the stability, it will collapse to the black hole. However, the rotation story is with this object, right? Right from the beginning. With the collapse, it starts spinning even faster than the original star was spinning before. And that's why the black holes inherently must have the rotation, and that's the reason why the Kerr metric is the right the model realized in nature.
Okay, so now we know how they do black holes form. Now I have the following question. We know that there is the black holes are covered with the horizon, and it was proven or mentioned since Mitchell that even light cannot escape from the black hole. So how do we know that black hole exist at all, since they are not observed in the using any light? Okay, so any even radio waves or whatever, any electromagnetic radiation cannot somehow be detected from the black holes. Professor Salzano, maybe you can deal with this.
From the perspective, we have, of course, indirect um, evidence for black holes. From the astrophysical point of view, maybe Professor Biesiada later can add something more. But I would say that, well, I will cite what was written on all the newspapers. We have an image of a black hole. Actually, is not technically correct because, as you said, if black holes cannot emit light, you technically cannot see them because there is no way for them to interact with light. But we have an image of a shadow which is produced by a black hole. And as far as we know, this picture perfectly agrees with the expectation which we had. I also, for this, I would like to uh, um,
You like ice
invite.
skaters? Okay, yes.
Yeah, no. I would like to invite the public, if they are interested, to watch this video because apart from the fact that you can put subtitles and you can also have it slower and see again and again and again, is from my perspective as a physicist, is a very clear description of what we should see about a black hole. So, in principle, let us start from something that generally, when we speak about black hole, people are just scared because they think about these black holes like sink, which start to take everything inside and nothing comes out. Black holes, if there is nothing around, they are just there. They are not starting to attract everything from everywhere and everything disappear. No. So generally, a black hole is just like this, a black sphere, let's say. And what appears here is the so-called Schwarzschild radius, which is the most famous horizon, probably the event horizon. What does it mean? This it means that in order to escape gravity, there you should have an escape velocity, which is the velocity which you need to have to free yourself from the gravitational attraction of a planet, of a star, which is greater than the speed of light. So as you can imagine, that's called the event horizon for a reason, because nothing which is, I don't know how to say, below this event horizon can be seen, because it cannot flow out. But this, in principle, we don't know what happens inside black holes. Very likely matter is destroyed, but what happens inside, this is one of the things which I never, when people ask me what is inside a black hole, I say I don't know. And anyway, if anyone, I guess that most of you have watched Interstellar, the movie, I bet for sure that you are not entering in the library of the bedroom of your son, of your daughter. I don't know what happens there, but that's the first horizon, and it is the most famous. But then, if you have a black hole like this, you will never see it. Why we can see indirectly effects of the black hole? Because at some point, it may happen. For example, we have a black hole in the center of our Milky Way. In the Milky Way, there is gas, there are stars. It can happen that while rotating and moving, they will arrive close enough to start to feel the attraction of the black hole. So what happens is what is here. Here, the title is a bit scary because it's written death by spaghettification. But what happens? So imagine that there is this star, which at some point during her life, start to feel the attraction of the black hole. What happens? It starts to go closer and closer, but until it reaches a certain limit, nothing will happen. I don't remember exactly how it's called, this limit. For in general, it's called the Roche limit. Roche limit is the distance from whatever, even from the Earth. You can calculate the Roche limit. Below this limit, if you have something, a star, a planet, it will start to be destroyed because the attraction, the gravitational attraction, will start to stretch so much the star or the planet that it will be destroyed. What happens with the black hole? That you have this, if the star approaches the limit of the black hole, it starts to form this. It's called spaghetti. I'm Italian, but it's not me who invented the term spaghettification, even if I like spaghetti. But why it's called spaghetti? Because the star, the material from the star is stripped in such a way that it becomes this long filament. And at some point, light, the star is not anymore there. What happens after? Well, theoretically, wait a moment, I'm trying to. Theoretically, the matter formed by this star will start to rotate around the black hole. There is, as you can see here, this light, this white ring just means, for example, this star has been destroyed and starts to rotate. You can see that here there is not any more matter. Why? Because this is another, let's say, horizon. It's called ISCO, innermost stable horizon, which means
circular orbit.
Circular, yes. It means that that's tricky because it's almost stable. Not exactly. What does it mean stable? It means that if there is something rotating in the inner part, if you perturb a little, it will stay there. But if you go beyond, then what happens? If you perturb a little, it will start to fall inside the black hole. Now, that's another horizon and works for matter. What about light? Light has no mass. So actually, there is another horizon. I want to say something. If the black sphere has the radius of the event horizon, this innermost stable circular orbit, technically, if the black hole is not rotating, is 3 times the event horizon. Now, what about light? Light can go closer. So let's say the innermost stable circular orbit for light is 1.5, more or less, so half. So it means there should be here at some point, yes, here. So let me show this. So this ring here now will be the photosphere, which is the closest orbit which light, let's say, in which the light can move around the black hole without falling inside. After this, event horizon falls inside. So as you can see, in this case of a non-rotating black hole, we have at least 3 horizon and 1 limit, because Roche limit, I don't know if it can be defined as an horizon. What happens when it's rotating is everything is distorted. Probably Professor Dabrowski can say more about how they are distorted, because honestly, I don't know. And maybe I don't know if I should continue, because you asked me to show how it is seen, a black hole, because actually you see a black hole because of this matter which is falling inside. So this matter is destroyed, is accelerated, it's heated, so it emits heat. And what at the end we can see is we have seen something with this experiment. This is called Event Horizon Telescope. event
Okay.
horizon because they
So
have,
we are slowly moving to the problem of detection by
yes,
the devices which are available on Earth,
yes.
which can,
So
yes. Mhm.
event horizon because they wanted to look at a black hole. But something which is strange here is that I brought telescope because this is how the collaboration is called. But as you can see here, this is a collaboration. It's not only one telescope. Why this? Because in general, the rule is the bigger is the telescope, the better. In this case, the source and the resolution which they wanted to achieve, and also the fact that this observation is in the radio waves, didn't allow them to build one single telescope large enough to watch to this black hole. So what they have done, there is a collaboration. Smaller telescopes put in different places of the Earth are basically equivalent to have one single telescope as large as the Earth. Actually, the thing is a bit more complicated because here there is something which technically is called very large interferometry, because what happens here is that each telescope detects an image, but it's a very poor image. But when you combine all of them with very sophisticated techniques, then you can see something. So what they have done is to look at the center of this galaxy. This galaxy is nothing peculiar. You can see it's just a bulge of stars, luminous stars. And when you start to look inside at the center, you see this image. So first, let me tell you that what has been achieved by the Event Horizon Telescope is something incredible, astonishing, because it is they have zoomed. And how much they have zoomed? Imagine that now on the moon there is an astronaut with an apple. If you were able to see with your eyes the apple, then you have done the same thing which the Event Horizon has done respect to this black hole. So just to let you know what is the scale of this observation. Now, initially in the newspaper, they say this is the first image of a black hole. Actually, black hole cannot be seen, but this is the first image of the shadow of a black hole. What we are seeing here is what? Do you see this part? This part is matter, which is orbiting the black hole, and it is what I told you before, it's heated up and it is very bright. What's very interesting is this other part, because this other part is not just the full ring. That's more complicated. This is probably Professor. I was not able to attend yesterday, but Professor Biesiada yesterday spoke about the gravitational lensing connected to how we can observe black holes. If not, I suggest you to we have a lecture in the Eureka channel where I personally discuss also gravitational lensing. So if you want, you can look there for more details. But basically, what is gravitational lensing? Gravity, which is this well, which we have seen before.
I mentioned
is able
this gravitational
lensing.
lensing yesterday during my talk about exotic
Okay.
objects. Yes, so the
So
audience can
basically,
refer to this. Yes.
what happens is that when light is passing through this or close to this hole, it's deviated. So even light can be deviated by gravity, and we see images like exactly in the same way we have here a lens. My glasses have a lens. They are not flat. They are curved. Why? Because they have to focus all the light rays. We can see things. Now, what is crucial here is that what you see here is the light distorted by the gravitational field of the black hole coming from behind the black hole. Just to let you understand another analogy, imagine that I have inside my head a light. In principle, I cannot see the light. But if I were a black hole, and there will be this very deep distortion of this space-time, then the light coming from here could be distorted because black holes are distorting so much space-time that they can bend light so much that the light coming from here is bent and I can see it. So what we are seeing here is like we are watching what is behind the black hole without looking behind the black hole, just because it's distorted. And just to conclude, again, I want to show you this picture from Interstellar. This is exactly the same. Of course, in Interstellar, they had video graphics, video makers, and they could make the picture better. What we had is a real picture. So there is noise. There are a lot of difficulties to get this resolution. This picture here is exactly the same which we got in reality. So there is a disk which is orbiting around, and then these up and down are the disk behind the black hole. And so, concluding, how do we know nowadays that we have black holes? First, because there are many indirect evidences, and then because we have even seen, actually not one, but twice, because we have also seen obtained the same image from the black hole which is in the center of the Milky Way.
Okay, and how about the picture which is behind me?
Well,
What
I don't know if
are these jets and how do they form? Okay, that's a
yeah.
provocation from me. So who can comment on that? Vincenzo or Marek? Yeah.
Yeah, well, I mean, let me just add to this the beautiful and pictorial description by Vincenzo that it is even more complicated. I mean, not only we are seeing the region of the disk behind the black hole because it has been lensed, bent. This is how the lensing usually acts, but at such close encounters of the light and the horizon, the light can be bent and turned back. I mean, so this normal, I mean, the bending angle, which is normally small in gravitational lensing, now it could be 180 degrees. They can get back. They can turn around and after one turn go to the observer. If it can get back, so only also the parts of the disk which we which are in front of us not only emit the light coming directly to us, but emit or illuminate the black hole, make a turn and go back. So, I mean, what we are seeing and what the Event Horizon team is confronting the data with the calculations, they are making a very precise calculations of all these effects. Of the models of the accretion disk emitting the light, illuminating this black hole, and what sort of the shadows can be produced. This is a commentary to this previous subject. Well, I mean, regarding yes,
I just showed what I presented yesterday during my talk.
yes,
Okay.
yes,
Yes. Mm.
yes, exactly, exactly. That's
That's a strong
this effect.
gravity lensing effect. Yeah.
Mhm. Well, I mean, but what is just behind you is a very beautiful picture. Actually, it is
Okay.
rather
Like
an
this.
artist's view than an actual observational data. But the observational data are very close to it, and every ingredient can be seen. So first of all, as Vincenzo told, there is a notion of the innermost stable circular orbit. It is not so much an horizon, but the place that, as Vincenzo said, when distorted a little bit, everything falls to the black hole and falls very quickly. So why this disk does not fall so quickly? Why it is not? And I am just, I mean, falsifying the myths that the black holes are the monsters that are just watching to devour everything in this surrounding. So, for example, if suddenly the sun, our sun, let's imagine, became a black hole with the same mass. Of course, we will lose the sunlight, it will be dark, but nothing else will happen. I mean, the orbit of the Earth will continue for billion and billions years to be the same, right? So, I mean, in each part of this disk, accretion disk, it is long living because it is orbiting this black hole. And by losing energy, by losing angular momentum, and they are losing because, I mean, the disk is a fluid. I mean, in a planetary system, we know that the Mercury and Venus moves faster around the sun than the Earth, and the Earth moves faster than the Jupiter, and so on. It is quite obvious for us, and the same holds for each part of this gaseous disk, each parcel. So, as Vincenzo said, this rotation is by no means uniform. The inner parts of the disk rotate faster, outer parts slower, and because it is a gaseous stuff, it is a friction between them. They heat up, as Vincenzo said, and this heat is releasing the light. However, it is one more ingredient beautifully depicted on this image. But yeah, I mean, this peculiarity, I haven't resisted myself on commenting on this, because you see that the closer to the center, this disk is brighter somehow, because I mean, this friction, this differential rotation gets more pronounced. But eventually, the rate in which it falls down is the rate at which the matter exceeds the innermost stable circular orbits and is being swallowed by the black hole, which happens very fast. So, I mean, we see the beautiful jets perpendicular to this axis, and this is something, I mean, typical to, we now know because of observations that in the cases of astrophysical black holes forming accretion disks, starting with the stellar mass systems, X-ray binaries. Uh, Even they are sometimes called the microquasars. So up to a quasars, which are the active galactic nuclei, we are sometimes and very often see the jet perpendicular to the axis. It is not 100% sure how these jets are formed in each and every detail of it, but one mechanism is invoked usually, which is called the Blanford-Znajek mechanism, which is the analogous to the Penrose process. I think that perhaps tomorrow, I mean, we will talk about the Penrose
Yes.
process in more details. But there is a
Mhm.
possibility, and this distinction between the ergosphere and the horizon itself makes it possible. I mean, this was the idea of Penrose, to extract the energy from the rotating black hole. And Blandford and Znajek have put forward the electromagnetic, I mean, version of it, strictly speaking, magnetic, involving magnetic fields, because just like the differential rotation in case of the sun that Vincenzo shown, it underlies the origin of the magnetic field of our star. So this phenomena of rotating and differentially rotating plasma inevitably leads to the formation of the magnetic fields, and the magnetic fields lines can be aligned along the axis and extract the energy very efficiently, as shown by Blandford and Znajek in the 70s of 20th century can extract energy of the rotating black hole. So this is another nice picture. So it is typical in the realm of galaxies and supermassive black holes, and I cannot resist to mention that in radio astronomy we sometimes see the so-called X-shaped jets, just like two jets shaped like an X, letter of X, which is being speculated that this is proof that in that particular galaxy, revealing itself as an X-shaped radio galaxy, there are a binary central black hole that after the merger of galaxies, which is a now well-established process in the formation of a large-scale structure, also the central black holes come close together, forming the binary system. It will be a holy grail for the LISA observations to detect the radiation from such a systems. But now these X-shaped radio galaxies are treated as a proof of this conjecture that binary black holes in the centers of galaxies really exist.
Okay, thank you very much for these comments. Okay, we are left with 2 or 3 minutes. I would like to, yes,
Curiosity to add,
yes, yes, please,
because
yes.
we have talked about these jets, no, coming from black holes, and compared to a galaxy, a black hole is small, but actually, the jets which come out can be as large as the galaxy itself. Because, for example, I will share a moment. Uh, Everybody knows probably that our Milky Way is a spiral galaxy, but actually, we should be better call it a ribbon galaxy because this is a representation of the Milky Way, and we now have direct evidence that there are these two lobes of gamma ray and X ray emission, which are as large as the same dimension of the galaxy, and they are produced exactly by the black hole which is in the center of our galaxy. So imagine the energies which are in play there, because such a small object can create these two lobes of a gamma ray emission, X-ray gas which heated, which is as large as the entire galaxy itself.
But small doesn't mean very few energetic. It
Actually, generally, it's the
contains
opposite.
huge energy and in fact huge energy density because everything is squeezed and the density is formally almost or formally infinite. So this object is really, really very, very contains a lot of energy. That's why actually it emits all this radiation. Okay, I have one speculation to give the taste also for tomorrow's discussion to our audience. It was mentioned by Professor Kiefer, black hole radiation, Hawking radiation. There are speculations that, for example, one can observe kind of emission of some black holes which actually explode, emitting this Hawking radiation, these small black holes which eventually form during the early stages of the universe, or even Roger Penrose has his idea of these eon universes, cyclic universe models, CCC, in which there were some black holes in the predecessor predecessor evolution, which now cyclically turned into our universe, where the black holes, in fact, exploded, or this Hawking radiation exploded and is visible in our universe. Could you comment briefly on that? What do you think? Is it is it is there any perspective to detect that or not? Marek, you have any opinion about it, or Vincenzo, or we will leave it for tomorrow to make.
Regarding the Hawking radiation, right?
Yes,
Well, I
because
mean,
there is a radiation and then there is last stage, which is a kind of explosion of the rest of this radiation. Mm.
yeah, I think that this reasoning is being used to actually make the constraints on the primordial black holes because, well, I mean, usual black holes radiate first of all with negligibly small. I mean, the temperature of this radiation and the energy is too small. It is totally suppressed by the background in the universe, so it is irrelevant at all. But the smaller the mass, the higher is the effect. So by calculating, I mean, what would be the sort of I mean, the range of the masses of black holes ending their lives during the age of the universe, we may, and taking into account that we are lacking the solid evidence explainable as the flashes or of such gamma radiations. It is often inverted as the constraint on on the amount of primordial black holes that have been produced. Uh, it is interesting to remark that when the gamma ray bursts occurred, I mean, first were discovered, it is known history, it was by accident by the satellites watching to the adherence to the anti-nuclear treaty between the Soviets and Americans. They discovered the flashes of the gamma rays from the universe, and then the targeted observatories, the most famous BATS experiment was launched to recognize them the better. But there were some opinions that perhaps this very short duration pulses of gamma rays could be attributed to the evaporating Hawking evaporation. Very soon thereafter, they were disproven. It was just, I mean, wishful thinking or science fiction behind. But I mean, some people were fascinated and put forward that this may be the case. Of course, we now know much better the origin of these events. For sure, they are not related to Hawking radiation.
Okay, thank you very much. We will likely be also mentioning this tomorrow. Tomorrow, as you see, maybe in my background, we will have the summary discussion. The discussion will be under the title "How to Practically Explore and Use Black Holes and Other Strong Gravity Objects in the Universe." And I would like to thank our guests, Professor Biesiada and Professor Salzano, for joining us today, and remind you that you were the guest of Eureka Foundation, Jerzy Stelmach Eureka Foundation. And I hope the audience will enjoy our tomorrow's last discussion about black holes, and all the films are available on the YouTube. Please visit our channel www.youtube.com / Fundacja Eureka in Polish. Name is in Polish. Thank you very much. Thank you, everybody, for joining us, also YouTubers, not only Zoom people. And see you soon. Goodbye. Thank you very much.
Thank you. Goodbye.